Welcome back to Tech Insights. Today, we're diving into the fascinating world of magnetic resonance imaging, or MRI. You might picture a giant tube-like machine, but MRI technology is actually racing in two very different directions simultaneously. On one side, we have the giants, ultra-high field MRIs pushing for incredible detail. On the other, a drive towards smaller, portable scanners making MRI more accessible than ever. Let's explore this engineering split. First, let's look at ultra-high field, or UHF MRI. These systems operate at magnetic field strengths of 7 Tesla and above, much higher than the standard 1.5 or 3 Tesla scanners found in most hospitals. Why go so high? The main goal is a massive boost in signal quality. This extra signal allows for images with sub-millimeter resolution, letting scientists and doctors see tiny brain structures like cortical layers, parts of the hippocampus, or minuscule blood vessels. This is crucial for research into diseases like Alzheimer's and Parkinson's, and for detecting small lesions in epilepsy or multiple sclerosis. Building these UHF scanners is an engineering feat, requiring huge superconducting magnets with complex cooling, advanced hardware, and specialized radiofrequency coils. But it's not without challenges. Higher fields mean technical hurdles like uneven image contrast and ensuring patient safety regarding absorbed energy. Plus, the immense cost, size, and infrastructure needed mean UHF MRI is mostly found in specialized research centers. Now, let's pivot to the other end of the spectrum, portable MRI. Here, the focus shifts from ultimate detail to accessibility and point-of-care use. These systems typically use much lower magnetic fields, sometimes below 0.1 Tesla. The engineering challenge here is getting useful images despite the lower signal. Key innovations include using permanent magnets, which cuts down drastically on size, cost, and the need for complex cooling. Engineers optimize these compact designs, and crucially, advanced software and artificial intelligence play a huge role. AI helps reconstruct images, reduce noise, and enhance quality from the low-field data. The big win? Accessibility. Portable units can be wheeled to a patient's bedside in the ICU or emergency room, used in mobile stroke units, or deployed in remote clinics or developing countries lacking conventional MRI. Systems like the Hyperfine Swoop even run on a standard wall outlet. This allows faster diagnosis for critical conditions like stroke or head injury, especially for patients too unstable to move. The lower fields also pose fewer safety concerns with implants. Of course, there are trade-offs. The primary limitation is lower resolution compared to high-field scanners. While great for larger issues like bleeding, smaller details might be missed. Scan times might also be longer, though AI is helping speed things up. So is it a race where one technology wins? Not really. UHF and portable MRI are pushing engineering boundaries towards different, equally important goals. Ultra-high field MRI seeks the ultimate anatomical detail, powering advanced research and specialized diagnostics. Portable MRI champions accessibility, bringing vital imaging capabilities directly to the patient wherever they are. Both paths are advancing rapidly, with improvements in hardware, software, and AI continuing to enhance both high-detail imaging and point-of-care solutions. Ultimately, they represent complementary tools, expanding our ability to understand the brain and improve healthcare, whether by revealing its finest secrets or making essential imaging available to all.